Part 2, this is for questions 21 to 30. Question 11, in which reaction does the oxidation number of chlorine change by the largest amount? Now let's look at the oxidation states of chlorine only in all of these reactions here. So for this one, of course, for potassium, since it is in group 1, that means the oxidation state is a +1, right? So that is a 1, then plus the one of chlorine, we don't know it, and then the one of oxygen is a -2, but there are 3 of them. Then we shall equate to 0 because this one is not charged, right? And then this will be -6 plus 1, that's -5. Then when it crosses, it becomes a +5. So that means this one is +5 here. Of course, here it will be -1, okay? Even here in a chloride, it is a -1. Here it is a -1. For the molecule, it is a 0, okay? Then, which other ones are we left with? Let's go to this one here. We have N, then plus -2 for oxygen, then is equal to -1 because there's this charge here. Don't mind about the number they have put here for balancing, okay? Then N shall be equal to -1 plus 2, and then this one will be +1. So this one is a +1 here, and that one there is exactly the same as this one here, because here there is a hydrogen ion and then that chlorate 1 ion. You see that? So we have that one there. Then we can see this one here also in here, okay? So let's look for its oxidation state. So N then plus 2 times the -2 for oxygen is equal to -1. Then N becomes -1 plus 4, and N becomes a +3. So that means here I have a +3, even here a +3. You see that? What is left? It is not the same as this. This one is an ion, okay? No. This one here is an ion, and this one is a molecule. So the oxidation state of chlorine here is N, then plus 2 times -2, then is equal to 0. Then N will be equal to +4. So here we have +4, and then here we have -1. Now, the change, we are looking at the oxidation number change, which is the biggest one. Of course, here I can say this is the oxidation number change is a 3. Is it a 3? 3 minus 1, what do you get? I mean, from 3 to -1, that means they subtracted a 4. So the change is a 4. Even here, I can say the change is a 4. You see that? Or actually here, I can also say that this 0 is changing to this. You see that? To a -1, not so? Yeah, to a -1. Actually, the best way to do this one here is to look at this one here, the change, because this one, when you look at this ion here, resembles this molecule here. So the change in the oxidation state here is going to be a +1. So that is a 1. And then here, that is a -1. So even the change here is a 1. Then the first one here, the change is going to be what? 5. It has to be -6. Not so. -6. So that means the change here is a 6. Then here, from 1 to -1, that is -2. So meaning the change here is a 2. And then also here, the change is a 2, from +1 to +3. Okay, then from 0 to -1, of course, the change there is a 1. It's a -1, but the whole oxidation number change is a 1. Then here, it's a +1, you see? So the biggest is here in the first one. So that means our answer is A. Question 12. Hydrogen is produced industrially from methane as shown in the equation. This is the one here. And then we are given the enthalpy of reaction. It's a positive. So that means the forward reaction is endothermic, and then the backward reaction is exothermic. Okay. Which conditions give the highest yield of hydrogen at equilibrium? Now here we are going to use the Le Chatelier's principle. If we alter one or more of the factors which affect dynamic equilibrium, then the position of equilibrium shifts to the side that minimizes the change. Now, when you look at this one, it is endothermic. Okay, that means first of all we need to shift the position of equilibrium to the right because we are getting the yield, the highest yield of hydrogen. Get it? So for the yield to go, for the yield to increase, the position of equilibrium has to shift to the right, and this one will be supported by the increase in the temperature because the forward reaction is what? Endothermic. So I have to look at high temperature. You see that? Then I look at the pressure here. We know that pressure, using Boyle's law, pressure is inversely proportional to the volume, and volume is directly proportional to the number of gas moles. So if you have many gas moles, that means you're going to have a bigger volume. You see that? Now, when we look at this, the number of moles that we are seeing this side, here we have 1, and then here we have 3. So 3 plus 1, we get a total of 4. And then this side, we have 1 here, and then 1 here. This one is 2. Now, here, since it is going this other side, the position of equilibrium is shifting to the right. This simply implies that we should do something here such that we go to the side of the volume being big. You see that? So for the volume to increase or to go to the side of many number of moles, now here, looking at this expression here or the relation here, you have to increase the volume. And when you increase the volume, because here the volume is increasing because of the many number of moles on the right side, when you increase the volume, then the pressure has to decrease. Then when you increase the pressure, then volume has to reduce. You see that? You look at if you are seated on your bed, right? It goes down. That means you're applying pressure onto it. So the volume has to reduce. Then when you stand up, you see it coming back. Okay, that means you have removed the pressure. So there is low pressure. That means volume is going to increase. So for this case, we have to look for low pressure. Okay, and it is here, low pressure. So our answer is therefore what? A. Question 13. W moles of nitrous acid undergoes a disproportionation reaction to produce U moles of nitric acid and V moles of nitrogen monoxide. No other nitrogen-containing product is produced. Nitrogen is the only element oxidized or reduced. Now let us write this equation here. Nitrous acid, then it undergoes a disproportionation reaction. You get nitric acid, and then you also have what? Nitrogen monoxide. Now there has to be something else which we are going to find out, okay? Because they said no other nitrogen containing compound. It doesn't mean that these are the only products that we are getting. Now let's check this one here. What's the oxidation state of nitrogen in nitrous acid? The one for hydrogen, it is a 1. Then for nitrogen is the one that we are looking for. Then for oxygen, it's a -2. Then we get to 0 because this one is not charged. So this will be -4 plus 1. Then that one gives you -3. So when -3 crosses the equal signs, we shall have a +3. So this one is +3. Then let's get for this one here, +1 for hydrogen. Then we are looking for the one of nitrogen, and then 3 times -2 for oxygen. Then this one is equal to 0. This is -6. Then +1, that is -5. That means when that one crosses, it becomes a +5. That means the oxidation state of nitrogen here is 5. I mean +5. Then this one here, we have N, then plus, this is -2, then is equal to 0. That means N is going to be equal to +2. So here we have a +2. Now, when you look at these ones here, we can see from this 3 to this, we are seeing a +2. Okay, the oxidation number change is a +2. This is what we call oxidation because there is increase in oxidation number. And then from here to this one here, it is reduction because it is from the big oxidation number to a smaller one. So that is reduction, right? And it reduces by 1. So if it reduces by 1, now I'm going to remove these signs. The change is 1 here, and then here it is 2. Are we there? Now that means when I'm balancing, actually that is what we call the disproportionation reaction. We are seeing a redox reaction, or one species is both oxidized and reduced at the same time. You see that? And we are seeing nitrogen here changing the oxidation states to +5 and then to +2. Now, when we are balancing using oxidation number changes, we get this change here. We look at this change that is here, okay? After getting this change that is here, then we also look at somewhere else where there is a change. Then we switch the numbers. Like for example, this one here is a 1, okay? Then I will go to this one here and I will multiply with this number here. So that means I will put a 1 here and then also a 1 there. You see that? Then this one here is 2. Then I'll go to this other one here where there is change and then I multiply by a 2. So that means here I will put a 2. But then when I put this number here, when I try to put this number, let's say 2 here, now I would have already violated this one. But then we have to balance these ones here. So if these are 2 nitrogens and then 1 nitrogen here, because here these are the numbers that are supposed to be there. Are we there? Then this being a 2 and this one being a 1, those are 3. So I'll put a 3 here. Now let us look at the number of hydrogens. These are 3, but here we have 1. So somewhere we have 2 hydrogens, okay, that are missing. Then let us look at the oxygens. This is 3, then times 2, that will be 6. This side we are having 3, and then 2, that will be 5. So there is 1 more oxygen. So 2 oxygens, 2 hydrogens and 1 oxygen. Don't you think we get water here? So that means water was the other product that was supposed to be formed. So looking at our answers, this is W, this is U, and then this is V. So 3, 1, 2, that is B. Question 14, gas X dissociates on heating to set up the following equilibrium. This one here. And then they are saying a quantity of gas X is heated at a constant pressure P at a certain temperature. The equilibrium partial pressure of gas X is found to be 1/7. What is the equilibrium constant, Kp, at this temperature? Now Kp, here, we are going to get the partial pressure of the product, okay? So that one of Y times the partial pressure of that of Z, then we divide by the partial pressure of that of X. Suppose there was a 2 here, for the number of moles here, then we would have raised this one to power 2, okay? But there is nothing like that, so that is the 1. Now, at equilibrium, if you are having the, remember, total pressure is going to be equal to the partial pressure of X plus the partial pressure of Y, then plus that one of what? Of Z. Are we there? Now, if, when you look at this one here, due to the molar ratio being 1:1 for Y and Z, that means the partial pressure of Y is equal to the partial pressure of what? Z. Are we there? Now, they are giving us this P as the total pressure because they say this one is 1/7 of what? Of the total pressure, constant pressure even. You see that? So, meaning we shall get here, total pressure is P, then this way, we are getting P of X is 1/7 of P. Then here we are having 2P. I can say 2Py because these two are the same. Okay. So take this one this side. That means we shall have P minus 1/7 of P, then is equal to 2Py. Then this one will give us 6/7 of P, which is equal to twice P of Y. So when you divide all through, that means you are going to get, when you multiply this one by 1/2, so the 2 will go here 3 times, right? So that means we shall have 3/7 of P. So that is the partial pressure of Y. which is the same as that of Z. Are we there? So meaning here we shall have 3 over 7 of P, then times 3 over 7 of P, then we divide by 1 over 7 of P. So meaning, what are we going to have here? This P can cancel with that, and then you have 9 over 49 of P, then times the reciprocal of this one here will be 7 over 1. And this one can go here 7 times, right? So that means the answer which we get here will be 9 over 7 of P. And that is B. Question 15. In the diagram, X is the Boltzmann's distribution for the energies of the particles in the reaction, and EA1 is the activation energy for that reaction. Then which statement is correct? Now let me start with this one that you know from the books. So you have, this is the Boltzmann's distribution. Here you have the activation energy, the minimum amount of energy required for particles to react. Now there is this one. This is the energy for particles with average energy. Okay, it's like in a class. I've always used this kind of explanation here. In a class, you do a paper and then you have very few people above 70% and very few above 30%. This is a normal distribution. Then we are going to find very many students in 40s, 50s, and 60s, right? Now, if the pass mark was 70%, and we are having these very few students here, then the teacher realizes that maybe they want to stream, they want to put in streams, and realizes that I'm going to have only 2 students, so we'll probably lower the pass mark. So if they lower the pass mark to 60%, then you'll get here, it will come here. Now, these other people that have been here have now added themselves to this class. You see that? So that means these ones who were having the average marks, that this group that was big now reduces. You see that? So therefore, when we increase the temperature, we are going to have many molecules with energy, okay, that is greater or equal to activation energy. So what happens is that this one here is going to shift to the right, and this peak here is going to reduce, because now we are going to have very few here with that energy, because you have gotten many which have gotten energy to react, which is bigger than the activation what? Energy. You see that? So this will be for T2, and this is for T1, where T2 is greater than what? T1. So it shifts to the right. That means at lower temperature, it will shift to the left. You will have very many with energy that actually doesn't make them to react, but the average energy. So they said that X is the Boltzmann's distribution for the energies of the particles in the reaction, and EA1 is the activation energy. So if this is our normal one that we are talking about, then for Y here, it has to be for lower temperature. Are we there? For lower temperature. Now, let's check here. Which statement is correct? EA2 is the activation energy at higher temperature. We actually don't draw activation energies for higher temperature. The activation energy is always here, okay? 1. But when you put a catalyst, okay, when you put a catalyst, then we put EA cat. Why? Because a catalyst provides a pathway with lower activation energy. So that's why you find that this activation energy for the catalyst is less than this one here, okay, for the reaction. So EA is the activation energy for the higher temperature. This one has to be off. EA2 is the activation energy for the lower temperature. That one has to be off. Y is the Boltzmann's distribution at a lower temperature. Y, this is actually the one that I talked about here. So this is correct. Let's check D. Z is the Boltzmann's distribution at a higher temperature. At a higher temperature, yes, it is supposed to go high here, but I mean, it is supposed to go to the right of this one, but the peak here has to be below this, because the number of molecules with the energy here, with that average energy, It has reduced. You see that? It reduces when it comes to this. Yes, you have increased the energy, but there are those few still that will be having that energy to react. Okay? Just like I said, you decrease the pass mark, you put it at 60. These ones who are in 50s and 40s are not going to be in position still to cross over. You see that? So that's why this peak is what? Lower than this one here. Okay, so therefore, what are we going to have? This peak here, you can see that it is above this one here. So that is why this one is disqualified. Question 16. Magnesium, aluminium, and silicon are elements in the periodic table. Each element forms an oxide. Which row is correct? Now they are saying here, the first one, magnesium is basic. Yes. Aluminium oxide is amphoteric. Yes, it can react with bases and acids. Then silicon 4 oxide is amphoteric. No, that one is not correct. So this one is actually acidic. Okay, silicon 4 oxide. You know, silicon is a metalloid. So it has some properties of metals and some properties of what? Non-metals, but more to the properties of what? Non-metals. So in the extraction of iron, if you can remember in your O-level chemistry, you had what we call extraction of iron from the blast furnace. Okay, so we had this calcium carbonate, which they add there, and then it is broken down by the fire. Then it goes to calcium what? Oxide. There's thermal decomposition here, then plus carbon dioxide. Then this calcium oxide here reacts with the impurity in the iron 3 oxide. Okay, it reacts with that impurity. The impurity is actually silicon 4 oxide. Now remember, calcium oxide is basic because when you dissolve it in water, you get calcium hydroxide, which is an alkali. So when this one reacts, you are going to form calcium silicate. Okay, this is the so-called slag, which is driven off at the end. You see, so this one is acidic. It's not amphoteric. It is acidic because it can react with the basic oxide here. You see that? Let's go to the next one. Magnesium oxide is giant ionic. That is okay. But then aluminium oxide is also giant ionic, but here they are saying simple molecular. This is an ionic compound because it is it is in between aluminium and oxygen, so a metal and a non-metal. But aluminium also has covalent character. It also has a covalent character when especially it is with a chlorine. So there is this one here. If it is anhydrous, it dimerizes, but if there is moisture, then it is aluminium what? Chloride. You go and read about that ammonia in your book, right? Okay, then here, silicon 4 oxide. It is giant, yes, but not ionic. It is giant covalent. And actually here, silicon 4 oxide has the structure of that of diamond tetrahedral. So oxygen, 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 then each oxygen, remember, it must get to what? It must bond, it must have these 2 bonds, 2 electrons needed. So this one will go to a silicon, and then this one continues like that. Okay, it continues like that. Now, so this is giant covalent, not giant ionic. Now let's go to wherever there is a cross, the option is off. Then magnesium oxide, because it is an ionic compound, it has a high melting point because of the strong electrostatic forces of attraction between the oppositely charged ions. The same for aluminium. Okay, but then silicon 4 oxide here, they are saying it has a low melting point. Remember, this one has a giant covalent structure. And when we are talking about melting points, we always talk about the structure and the bonding. So if the structure is giant, automatically the melting point has to be high. Why? Because you have a lot of energy to apply in order to overcome the strong intermolecular forces of attraction. So in here, there are strong intermolecular forces in here that are holding this one here. So therefore, this one cannot have a low melting point, the fact that it is a giant, right? Then let's go to the last one. That means the answer is actually D, because the rest here have gotten across somewhere. Magnesium oxide is slightly soluble in water. Oh, there's a slight reaction with water. Yes. So we get magnesium here. If it is cold water, then you are going to get what? Magnesium hydroxide and hydrogen. But with the steam, you instead get magnesium oxide and then hydrogen. Aluminium oxide, no reaction with water. Yes. That is why we have power cables. So the aluminium reacts with the oxygen, then it forms a layer there, these overhead power cables. Then that layer which is formed protects the wire here from any further reaction. So even if it rains, we still have the wires there. You see that? Then next, we have no reaction with water, silicon. Yes, this silicon here, silicon 4 oxide, is insoluble in water. This is true because you remember, if you have silicon 4 chloride in the periodicity, okay, then you react with water. There is hydrolysis here which takes place. So you have silicon 4 oxide, then plus an acid here, which is HCl. These are steamy fumes or white fumes that come off. To balance this, I will put a 4 here and then I'll put a 2 here. So this one is insoluble. It comes off as a white PPT. You see that? So no reaction with water. You see that? A precipitate doesn't dissolve or react with water. You see that? So that's why our answer is D. Question 17. Which statement correctly describes what happens when silicon tetrachloride is added to water? This is the exact thing I've just talked about here. Imagine. This one here is what I've just talked about. Wow. So since here we are having HCl that comes off, okay, it will dissolve in water, then you will form an acidic what? Acidic solution. You see that? Or did I write acidic acid? It is acidic what? Solution. This one is a white PPT. Now the options here. Silicon tetrachloride, by the way, it is a liquid at room temperature. In one of the questions they have ever asked about its what? Its state, okay, at room temperature and pressure. So the silicon tetrachloride dissolves to give a neutral solution only. We can see this is an acidic solution, okay. Then here reacts to give an acidic solution only. Yes, there is an acidic solution, but there is also white precipitate. This one will just settle down or will move through the water. You see that? Then this one here reacts, it gives a precipitate. This is the one, and an acidic solution. Don't you think the answer is C? How about D? This one reacts to give a precipitate and a neutral. No, acidic. So we were supposed to look at acidic. Then there has to be a precipitate. Question 18. X and Y are two elements from period 3 of the periodic table. Element X has a higher electrical conductivity than Y. Now let us look at what we are having here. Magnesium has a higher electrical conductivity compared to sulfur. Then here, magnesium, of course being a metal, also has a higher electrical conductivity than that of what? Silicon, because silicon is a metalloid. You see that? It is actually more of a covalent element. Then sodium and chlorine. This sodium is more conductive when compared to what? The chlorine. So that is okay. And then here, these are non-conductors of electricity. So that means I'm going to put off this D. Now I'm supposed to look at these three here. Let's go. They are saying also that element Y has a higher melting point than X. So here I took X to be this. Okay, that is the X. Then Y has to be this, Y has to be that, Y has to be that. Now, sulfur doesn't have a higher melting point than magnesium because this one is simple molecular. Simple molecular has 6 copper 8 covalent bonds that keep the sulfur structure there. Then that means this one is off. Then you come to this one here, silicon. When you come to period 3, we have, if this is the these are our axes, sodium is a metal, so it has a higher melting point. Then it increases to that of magnesium, then aluminium, then silicon shoots so high, and then we come back to fluorine being, because it has a simple molecular structure, P4, then we are going to have it below the sodium here, okay? Then sulfur here goes up, it is S8, so we have more electrons, or we have more covalent bonds. Like I said here, it is S what? It is S8. It has actually a structure of that of a W. It is like that. So S, 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 S. You can check it on the internet, you will see it. Okay. Then after that, then we go to chlorine because it appears as a gas at room temperature. Then it is down here below this one of what? Of phosphorus. And then argon is also below that one of what? Chlorine. It is a gaseous what? Monoatomic element. So silicon has a higher melting point compared to magnesium. So there is another tick here. That means our answer actually is supposed to be B. This chlorine here, which is here, its melting point is below this one of sodium. You see that? So that is why our answer is what? B. Question 19. A sample consisting of 1 mole of anhydrous calcium nitrate is completely decomposed by strong heating. What is the total amount of gas produced in this reaction? Now, when we decompose group 2 nitrates, we get the oxide of the metal, that is calcium oxide, then plus nitrogen dioxide, okay, as a gas, then plus oxygen as a gas. This is a solid, this is a solid. Now, to balance this, if there are 2 nitrogens here, that means I will put a 2 here. Oxygens are 6. This is 1 plus the 4. Those are 5. That means I will put here a half. This one has to be 1 because they said 1 mole. Otherwise, I can multiply all through by 2 to eliminate this denominator here. And then you find that you have a 2 here, a 2 here, and then a 4 here, then here 1. You see that? So that means the total amount of gas produced here, there is a 2 here, then plus the 0.5, which gives us 2.5. And therefore, our answer becomes a C. Then question 20, steam is passed over heated magnesium to give compound J and hydrogen. There is somewhere I talked about it. So when you get magnesium and you react it with steam, that is water, which is gaseous, you get magnesium oxide, solid, then plus hydrogen gas. This one is a fast reaction, but magnesium reacts slowly. Okay, magnesium reacts slowly with cold water. So here water is a liquid to get magnesium hydroxide. Okay, then plus what? Hydrogen. This one is sparingly soluble in water, and the solubility of group 2 hydroxides, it increases down the group. So this one can be, you can see that white something, white precipitate in there. So it slowly dissolves in what? In water. Now, they are saying what is not a property of compound J. So compound J is magnesium oxide. Here they are talking about Mr. What is the Mr here? The AR of magnesium is 24.3. Then plus that of oxygen, which is 16. This one gives us 40.3, which is exactly this one. So A is okay. It is basic. Yes, magnesium oxide is basic because when you put it in water, you're going to get magnesium what? Hydroxide. And the hydroxide is a basic what? Is an alkali. Okay. Then it is a white solid. Group 2 oxides are white solids. Okay. Most of their compounds are white solids. So even this one is okay. Then it is very soluble in water. No, just like I said before, that magnesium hydroxide is sparingly soluble in water. The solubility of group 2 hydroxides decreases down the group. The explanation we give it in A level in terms of lattice energy, enthalpy of hydration, and then enthalpy of solution. So that's why our answer is what? D.